Mhm.
And maybe may I have may I have introduce you first, dear hello everyone. Uh, Today we have we very pleasure. It's our great pleasure to invite Professor Andrew Dorogovtsev to give us a series of lectures uh, on self intersection local time. Please allow me to introduce Professor Andrew. Uh, Professor Andrew Dorogovtsev received his PhD from the Institute of Mathematics, National Academy of Science of Ukraine in 1991. Now, Professor Andrew is the corresponding member of the National Academy of Science of Ukraine and the head of the Department of Stochastic Process Theory of the Institute of Mathematics, National Academy of Science of Ukraine. Professor Andrew is mainly engaged in the research of probability theory and the related fields. He is one of the academic leaders in the field of probability theory in Ukraine. He has published more than 100 papers in top international journals. He was invited speakers at many international conferences. At the same time, Professor Andrew is the editor of a series of stochastic process, Ukraine Mathematical Journal, and other journals. Now let's welcome Professor Andrew. And I think it's your time. Hi.
Okay. Thank you very much for nice introduction and for the invitation. For me, it's always a pleasure to make lectures in Engineering University, and I hope maybe next time, time of the next time, I can do it not online, but exactly in Chechnya. Also hope that representatives of Chechnya University visit me in Kiev, and I hope that this lecture will continue our fruitful collaboration on probability theory. Let me start today with the outline of our lectures. We will study with you some approaches to understanding geometric properties of random fields and random processes. Briefly, the main problem which will be discussed during these lectures can be described very easily. Suppose that we have some domain D in Rn. This is connected open set, like this. This is D. Then suppose that we have a random field psi. This is a random field. When we discuss different random fields, I will think that psi can take value in Rn. So psi can be considered as a random value from D to Rm, and can be different from N. So what we have here, we have here mapping to R M, and here in RM we get a random image of D. So here I write something like this.
Hi,
This
Professor.
From D.
Hi, Professor.
Yeah.
Maybe the camera move to the left or right, as you can see. Yeah.
Правее чуть-чуть. Не, вправо не видно правой части.
Вот так?
Нет, то, что вы справа написали, не видно.
А так?
Еще чуть. Может быть, ее пододвинуть немножко, если она, или там она накрылась.
Пододвинуть вперед?
Вправо. Вправо.
Так.
То, что справа написано, не видно. Вот. Вот.
Yes.
Еще чуть-чуть. Вот так, да.
Okay. Okay. So we have a random field, which is considered as a random mapping. We have the image of the domain D under the map side, and suppose that we have here some point y 0. This will be for us some fixed point from R. The main question which we will discuss during our lectures is the following. Can we find probability that psi from D contain our y0? This will be the main object of our consideration. We will discuss methods, how we can guarantee that this probability is positive. We will discuss the properties of the random field psi, which leads to the possibility to make the conclusions about this probability. First of all, let us think why such probability can be interesting, and why to find such probability is not too easy. Let me give you some examples. Of course, we will discuss later strictly formally all these things which I will discuss now. But now this is just introduction. So suppose that we have winner process W T belongs to 0, 1, and this is winner process. In us. Then one can ask about the following things. The first one. Does winner process hit fixed point in R? So what is the probability that winner process 0 will contain some point like 0. Let me note that this question is complicated due to the following reason. For example, one can think in the following manner. Okay, let us fix something. Let us fix something. T belongs to 0, 1. Suppose that y0 is not equal to yes. Then it is easy to check the probability that W for fixed T is equal to y0 is equal to 0. It happened because WT for T greater than 0 has an absolutely continuous distribution. It has density. So probability that this vector will be equal to fixed point is equal to 0. From other side, maybe it can happen that trajectory of our linear process will hit the point y0 at some random moment of the time. And to answer whether or not it happens is difficult job. We will see. In such a very simple example, we see that even now this question is related to the properties of all trajectory of the process. So when we will discuss our question, it will be related to properties not of the fixed values of the random process or random field. It will be related to the trajectory of all random process or all random field. Excuse me. Катя, у меня сейчас лекция будет. So we can see that in this case, the question is related to the behavior of the whole trajectory. Next example. Suppose that we consider linear process in dimension 2. In R2. Then one can think we usually use linear process in such manner that W is just a picture of random motion of the particle in the space. Then the question arises, is this picture adequate to the nature or not? For example, here I draw self-intersection of the trajectory. Does it happen or not? This is the question. And again, we understand that this is a question about the whole trajectory. not about the fixed values. For example, if we take WT1 and WT2, we understand the probability that they are equal. Equal to 0 when T1 is not equal to T2. Again, because the difference also has Gaussian distribution, which is significant. So, again, the question about geometric form of the trajectory of the Wiener process leads naturally to the following reformulation. Let us introduce random field psi, which will depend from two parameters T1 and T2 as follows. This is just the difference of WT2 minus WT1. There, one can see that psi is a random field defined on the set D equal 0, 1 square, 0, 1 square, and the question about the self-intersections of the trajectories, existence of the self-intersection of the trajectory of time is related to the probability that psi of D exclude diagonal. So D minus the set DT is equal contain 0. So you see that discussing the properties of the trajectories, not only Brownian motion, of different random processes, we can introduce random field related to differences, for example, and then one can discuss the existence of the self-intersections exactly in the same manner as we formulated our main question. Does some fixed point belong to the image of our random field? Now, let's go faster. Suppose that psi is smooth field. For example, D. Then, of course, psi can be psi of D can be considered as n dimensional manifold we suppose that m now is less. Then the question about the containing of some pointwise can be discussed with the, let me draw it. Now this is our side of D, and this is our y0. So one can try to calculate the distance to our manifold. Our manifold is smooth. Then this distance can be calculated using stochastic geometry, stochastic differential geometry tools. So in this case, the solution to this question will lead us to the development of some differential geometry for stochastic manifolds in Euclid space. This is about the motivation of our question. We will see that a lot of geometric problems related to random fields can be reformulated in such. What is this problem? Now let's see what we can do. How one can try to answer this question. Let me begin with the example. Suppose that we have now one-dimensional linear process. And we want to ask if I have x y0, which is not equal to 0, what is the probability that w from 0, 1 will contain our y? How one can proceed? In this one-dimensional case, there are different solutions to this problem. Even this probability can be calculated exactly. But now let us check more simple statement. I will check that this probability is greater than 0. Only this. But doing this, we will develop some good tool which can be applied in more complicated situations. Let's start. What I will do? Let me consider the following function. H epsilon of x will be equal 1 to epsilon. Here is the indicator of y0 minus epsilon, y0 plus epsilon from x. One can imagine the graph of this function. here is y0, here is a small interval around y0 of radius epsilon, and then we have a large attribute. Here is 1. One can check that due to the such choice of the sides of this rectangle, we have the property that for every f which is continuous and bound on the set of real numbers, we have the following. The integral, this function f of x, h epsilon of x dx converges to f of y g. It is easy to check, and please do it by yourself. Then one can try to calculate, or just first to consider the following random variable. I will denote it by eta epsilon, and it is equal to the integral from 0 to 1. Here we have h epsilon from wt dt. Of course, in such integral, there are anything difficult because we know that W has continuous trajectories, so this integral is well defined. Moreover, we can try to find expectation of eta epsilon, and this is what? This is integral from 0 to 1 expectation of h epsilon wt dt. It's equal to, we know that Wiener process, standard Wiener process, has values at the moment t, which has density. Namely, we know that wt is normally distributed with 0 near variance. Consequently, it has probability density pt of x, which is equal to 1 to the square root of 2 pi t multiplied by the exponent minus 1/2 of x squared. Excuse me, with t minus 1 to t at x squared. So that one can substitute this density to this expression. And we will have the following formula. It will be like integral from 0 to 1 integral r. Let me keep the notation pt. It is not very important right now, the precise form for the density. So I will write the expectation in the form hx and h epsilon x, pt of x, and then dx dt. Now, let me recall you the main property of our h epsilon. Here it is written. We know that h integral is h epsilon tends to f0, f from y0. So one can say that when epsilon will tend to 0, our expectation of h epsilon, tends to integral from 0 to 1 pt of y0 dt. This is the final value. One can easily check this using now the form of pt. It is fine. So at least mathematical expectation of eta epsilon converge. More, not only mathematical expectation, one can consider the second moment. I will do this for eta epsilon square. It can be done for the product eta epsilon 1, eta epsilon 2. But for us, this is enough because today we have an introduction. We just see. So let us check what is it. It will be like double integral. You remember expression for eta. Here is h epsilon w 1 multiplied by h epsilon w t2, and here is expectation, and here is d1 d2. This is the expression for eta epsilon square. And again, one can calculate. It will be integral from 0 to 1. Here is double integral, which is respect to r, and we already know that for t1, which is not equal to t2, wt1 and wt2 has future density. So I will consider such image. Then failure wt1, wt2 has density again. It is not necessary to write its form, but it will be useful exercise to find the density of this frame. And I will denote this density by qt1 2. Then I can put it here, and it will be like h epsilon x1, h epsilon x2, and here is q t1, t2, x1, x2, dx dt. Again, you remember properties of H MC. Then one can imagine that when we have such expression, when we have H epsilon from different variables x1, x2, and continuous bounded function from x1 to x2, the answer will be the same, but epsilon tends to infinity. So it tends, let me write something. It occurs that it tends to integral from 0 to 1, and here is q t1 2 from y0, and here is t. And again, it can be checked that this integral converges. From these two things, one can say that there exists a2 limit, and the epsilon tends to 0 of eta x. Let us denote it by eta 0. And now it is crucial moment. It occurs from the existence of this limit and non-zero expectation. We can make our conclusion about positive probability to visit y0. Let me show you why it happens. For example, suppose that probability that W of 0, 1 contain y0 is equal to 0. So just suppose this for a moment. Suppose. Then what we can conclude? You see, W is a continuous function. We mentioned this. So this image is a connected compact set. And we say that with probability 1, it does not contain this point y0. It means that the distance between y0 and this W01 is greater than 0 with probability 1. Yes. Let me draw a picture. Suppose that here we have y0. Maybe here we have y0, and this is an objective, typical objective of W on the interval 0, 1, and we know that this distance is, so it happened like here with level y0, we do not hit, it does not hit. Yeah? Then, because of the positivity of It happened that when we take sufficiently small epsilon, and organize such a corridor around the level y, then this corridor and our trajectory do not intersect. It means that due to this picture, eta epsilon begins to be equal to 0. Yes? Because you remember expression of eta epsilon. It contains the integral from h epsilon. H epsilon is the indicator exactly of this interval. We have no intersection, we have 0. From here, one can conclude that this hypothesis leads to this conclusion and leads to the following conclusion that eta epsilon, eta tends to 0, and epsilon tends to 0, so from this we have this. But here, you see, we have the limit eta 0. Of course, in a two sense. But we have a risk theorem. We say stuff. We have subsequence. Eta epsilon n, which goes to eta 0 when n tends to 50 everything. And you see, this eta 0 must have non-zero expectation. But here we have this one. We have a contradiction. By this non-zero expectation, this eta 0 must be non-trivial random variable. But this supposition leads us that this random variable must be trivial. So here we understand that considering this random variable h epsilon, we can say something about the probability that our trajectory hits y0. Yes, with positive. This is an example. But consider this example, we introduce this eta epsilon. We call this integral 0 to 1 h epsilon wt dt, and now one can ask how we can move this approach to other processes, to random fields, and how it works for smooth random fields. So let us check this. First of all, let me introduce good notations, which will allow us to consider generalizations. So you remember main property of these functions h epsilon, namely following functions which is continuous and bounded on the we have the integral with respect to r h epsilon x f of x dx tend to f y0 when epsilon tends to we can consider this relationship in terms of generalized functions. Here we have the action of function h epsilon on function f, and it leads to the such expression. And what is the tool which take the function f and put it into correspondence in the fixed point? Usually, in the theory of generalized function, in the physics, people say that this is beta function. So the right notation for here is the beta function concentrated at the point y from f. This is nothing else as f of y0, but for special f. We have some restrictions, not for everything, some restrictions. If we will use this notation, then one can say, at least formally, that here we have the following limit when epsilon tends to 0. We have here integral from 0 to 1 beta y0 wt. Such expression occurs to be very fruitful in a sense that it allows us to make a lot of half of form calculations and a lot of generalizations. So it is useful and we will use it further. More, this thing has a special name. Before to introduce this name, let me compare this integral. Consider the form. The integral from 0 to 1 indicating the point y0 from wt dt. What is this? What is this? This is nothing else than the time which our winner spare at the point yc. Yes? We just calculate moments when wt is equal to y0 and then take a step. But unfortunately, this total time equal to 0. It's equal to 0. Yes? Every step. And to understand this, it is trivial. Yeah? Just take mathematical expectation. This integral and it will be equal to the integral from 0 to 1, and here the integral is r pt x indicator of 1 point y0 of x dx dt, and it is trivial that this indicator is equal to 0 with respect to the back measure. So we have inside 0. So so if we try to define the total time which is spent at the point y0 is 3, even after we proved that we visit y0 is positive. So we need to find some another way to measure time which we spend at the point y0. And this is the right way. This limit is called local time. Local time of W of W at the point y0. Of local time, it's and the local time for different processes and different random fields will be the subject of our investigation too. We will see that it is a continuous function of good processes. We will see good formulas which allows us to investigate the behavior of random field or random process using this local time. And we have seen that if this local time is not 0 at the point, then process visits this point with positive probability. So we can say something about trajectory of our process using the local time. Now, let us check. Does it work for smooth function? Because this substitution, when we substitute those on this one, it seems from the first look artificial, and we need some examples to understand that this is natural characteristic. It can be introduced and it can be investigated, and so on. So let's check what does it mean for smooth functions. So forget for a moment that we work in the random process. Just take smooth function, deterministic. I will consider the function f, which is C1, 0, 1. And I will take such a point y0 z for vertex which belong to pre-image of f of y0, then derivative is prime of x is not equal to we will see this condition a lot of time in our lectures. It is interesting that we can for sure say that a lot of points have this problem. Of course, if the function is not constant. This is interval. This is the graph of our function. And in this picture, what I can take, for example, this line here, yes, but I cannot take this one, yeah, which is related to some local x. This is my function. And it is interesting that in our lectures we discuss things which are in between the usual differential geometry and stochastic process theory. So here is a time when the usual differential geometry arises, and it says that there exists Sartre theorem, which says exactly that for arbitrary, even for the constant function f, the set of functions such that here we have at least one, the set of points, at least one, such that here we have equality to zero, then lambda of such y0 is equal to 0. So the back measure of this extreme points, like this one, is 0. On this graph, it is trivial because this is, those ones, so we have just find it. But it works in the multidimensional case too. But nevertheless, I take such y0 that we have not equal to 0, derivatives. Then, see what happens when I want again write eta epsilon. Eta epsilon should be equal to integral of 0 to 1 h epsilon f of t t. I can write it. Yes. So what happened? I will take this small corridor. Then I am calculating time related to the times which our functions spend inside of the group. This one, this one, this is the part of the graph of our function which we need to solve. And this is our total time. And what we do after we divide it on the length of the corridor. So this is trivial. This is from first course of calculus. What we just take the increment of the argument and divide on the increment of our function. So finally, it goes to the following sum. The sum of the pre-images of f of the point y0, and here's one of the normal f of x. Here is the answer. So you see, please check it by you see, the local time exists for the smooth functions too. So we will use this formula it will lead us to the rice formula. We remember I already gave some lectures on the rice formula. So memorize it and you use the connection between them. Today, what we discussed the question about the image of the random field containing some fixed point. We understand that this question is related to the total to the geometry of our random field, and we understood that one can try to check the answer to this question using the new notion of the local time. We introduce this notion of the simple examples, and we even see that it works. It gives us the right answer for linear process, for example. Also, we see that this local time can be defined for smooth function too. So maybe this is some universal object. And our plan for the next lecture is to study fundamentally the notion of local time, to understand for which processes random field it exists. And after this, we will make conclusion about the geometry of the images of trajectories, of random fields or processes. For today, we finish our work. Please, if somebody have questions, please.
Oh, thank you, Professor. So, any question? Oh, if no, maybe we can end today. Yeah.
Okay, so at Wednesday, and we will continue with studying step by step the notion of the local time.
Yeah. On Wednesday, it should be 21st, right? The same time. Yeah.
Yes, at the same time.
The 21st. Yeah.
Okay.
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 Thank you,
See you.
Professor. So see you.